Okay, welcome everybody to the third lecture, I guess, or third session of our workshop to introduce you to supercomputing. This is not the right slides. Hold on. Here. Okay. There we go. Excuse me. Okay, so welcome again to the third session of Intro to Supercomputing.
Hello.
Can you? Sorry. Yeah. So we're going to wrap it up today, and so we're going to look at the assignment again that was given on basically on Wednesday. We're going to look at some common mistakes. We're going to give you a solution. So if you didn't quite get there, at least you know how to get there. And then if we have some time, I'd like to go over some best practices of scientific computing, either in a supercomputer or elsewhere. Things that a lot of us, and with us I mean the analysts at SciNet, have had to learn through making the mistakes, and so some tips that can make you more effective in your scientific computing endeavors. So I think I mentioned this before, but the whole point of the assignment is not to get it right or to get it complete. Of course, that's what you would strive for, but to make sure that we know that you've worked with the material, that you've learned something, and that you were engaged, because it is a little difficult to ask if you are stuck at some point to figure this out in just basically 2 days. So that's not the point. The point is really that you've attended the meeting. That's why we've attended tests, and that you've engaged with the material. By the way, if you haven't submitted anything yet, you still have a chance to do so. I think the Dropbox is open for another 7 days. So feel free to either submit an improved version or not. I don't think we'll have time to give you feedback on it, but we will look if anybody else submitted something that is an assignment. Okay. Now we have about 30 or so submissions this morning. I went through them. Many of you, pretty much most of you, got this perfectly. So that's nice. I see in the chat there's some issues with the attendance code and that it is not 5. So I'm going to have to check that in a second. But hold on. That is strange. Anyway, so that's the point of today, to go over the answer and to go over the assignment. So what did we have to do again? So we had this calculation that we were doing that is bond break. It was simulating the breakage of a chemical bond, and doing that for a number of cases, 96 to be precise, and just basically record the time of breakage. And they could all run in parallel because each of them is a separate simulation that spits out its own output and has its own results. So they could run in parallel by using several cores at the same time. However, the script that we had just had a serial loop going over all of these repetitions, and each repetition had to be finished for the next one to start. So the idea was to use GNU Parallel to parallelize this and to make sure that 16 of these simulations would be running at the same time at all times. And so that's the number 16 is here because there are 16 cores on a compute node in our teach cluster. So that way you could ask for a single node with 16 cores, and that would do. And then the question, of course, is how much faster that is. let's just figure this attendance code thing out. Strange. Is there anybody who got the number 5 as being correct? So just want to know if this is a an issue with just a few people or with everybody.
Says I tried and it's still, yeah, it shows that the answer is wrong. I looked into the test, so you can continue. I will update in the chat, so don't worry about it.
Okay, all right. So it seems to be systematic on our end, and Marcela's looking into it. So keep attending, and then we'll get you the right code towards the end. Okay, so the point was to get speed up, to make sure that this happens and that it happens properly. So here's one answer that worked for me. This was our initial scripts. Remember, we're loading Python, or maybe it was Python/3. That's the default now anyway. A temperature value was set in this variable t, and another variable s, which is the seed values, ran from 1 to 96. And for each of them, we run one break with that specific temperature and that specific seed, and with file names that depend on that temperature and the seed. The temperature is not varying here, so we could have hard-coded 2.2, but we can imagine that we might want to also sweep in the temperature direction at some point. And then the log file is where we would find the breakage time, and so that's what this awk statement does. It basically fishes out the picks out the breakage times from the logs of each of the files and just prints them out. And so if you've aspatched this on the teach cluster, and then you get that number that is the job ID number, and then after it's done, you say SEFF, so I guess slurm effective or something, SF, and then the number of the ID, so the job ID. It would have told you that it takes about 15 minutes. It varies a little bit how long it takes, which is a bit strange perhaps, but it's mainly because the writing of these files has to be to a shared file system, and there is some fluctuations in how fast the file system is depending on how many people are using it. And this is a little bit more of an issue on the teach cluster, whose file system is a little bit less performing than that of our main supercomputers. So if you got 14 minutes, possible. If you got 17 minutes, that's still within the realm of possibilities. So to parallelize this, we use GNU Parallel, so we have to load the GNU Parallel module. We have to ask for 16 tasks on a node and just one node, which is also the default. So you can leave out a node equals 1, but it's good to be explicit so that you take a full node, and on that full node, you're going to run 16 tasks at the same time. So these tasks are the sub jobs that GNU Parallel is going to launch. Okay, and yes, so Parallel is you have to sort of figure out the syntax. We went over that last time. You have to give it a command. So that's basically a template. So the command starts here, bond break. That's just temp, and then a temperature value, which it takes from just the bash variable $t here, and a seed, which I've set to $s here, but I think that is a typo in the slides. This should be curly braces, right? That's how this is supposed to work. If it's not curly braces, it will actually not work because there is no s defined. So this should be a curly brace, and the file names do have the proper curly braces here. And those curly braces are going to be replaced by the values that this template parameter takes, and those follow the triple colons in the syntax of GNU Parallel. And so that's 1 to 96. So this is a list from 1 to 96. Each of those values, one by one, will be inserted into this template. So that constructs all of the commands we want to run. Parallel does the construction. And then GNU Parallel will start the first 16 of those in parallel. How does it know it's 16? Because it's actually nicely incorporated with the scheduler, and the scheduler tells it that there are 16 tasks available, so parallel picks that up in this case. If you're in a system where that isn't integrated like that, you would have to say -j and then the number of simultaneous subjobs. Okay, so that runs 16 things at the same time. Once it's done, it again collects all of the time, so you should get essentially the same output. And in this case, this took 1 minute and 10 seconds for me. So that's about a 12 times speed up, and that's not bad. Let me see if there are any questions. Okay, so if that's clear, that's good. I see the attendance code has been worked out. That's interesting. So this is a solution that works. Let's look at some things that might not have worked, or because the solution is not unique. So here's a few common issues that I found. Oh, what is job log? So job log here is a parameter to the GNU parallel command. I have no GNU parallel command on the left, and therefore there is no job log there. But what it does is it creates a file. The file is called log.txt, and for every subjob that GNU parallel starts, it puts in an entry there saying that it's first that it started, and then when it's done, it will give it will say that it is done in that log, and it will also say how long it took and a few other parameters like when it was started, etc. So it's a very useful way to know what's going on while GNU parallel is doing its job. It's also a way to make it possible to restart failed jobs, but I'll get to that later. So this creates basically an on-the-fly log of what jobs are actually running or have started or have finished. And it does not contain the ones that haven't started. So it's a way, if say, for instance, it turns out that this takes more than the 20 minutes we asked for, we would get a failed job, but not all of the jobs will have failed, not all of the subjobs will fail. And so we can look at the job log and see which ones were successful and which ones were not. Any other questions about this solution? There's a question how you copy from scratch to your local machine. Yes, so you can use anything that can use scopy or SFTP. MobaXterm does have a built-in way to do it, but I'm not too familiar with it. What is important to realize, though, is that if you are on the Teach cluster, so this is true for $scratch or $home or any of your system files on the Teach cluster, and you're logged into the Teach cluster, you're in a prompt that runs on the Teach cluster. So what you're asking, if you want to copy from the Teach cluster to your machine, what you need to be able to do is to somehow reach your machine from the Teach cluster. If your computer isn't accessible on the internet by its name, if you can't connect to it from the internet to your machine, and for most like home machines this is true and you want it to be true, then there's no way for the Teach cluster to know where you are. So there's no back channel that says, oh, copy it back to where I came from. No, you're logged into the Teach cluster. So the way you would normally copy things off of a shared system like the Teach cluster is to start back on your local machine and start either an scopy command, or you can use FileZilla, or you can use SFTP and copy it such that you specify your source as a remote source. So that's that. So that is the Teach cluster, and then your target is local. So it seems a little counterintuitive, but you're basically pulling things off of the Teach cluster. Okay, good question. Why is there a speed up of 12 times? So and not say 16, right? So if you typed SF and a number, it would give you not just the time it spent, but also the efficiency, and it will say something like 80%. And so what happened is that at some point we're running out of jobs. So we have 16 jobs running all at the same time. Let's say the last 16, one of them finishes and the others are still going. We will have a core that for a little while is not doing as much as it could, because there's nothing left to do. So it's not really it's not terribly bad because there was nothing else to do. But that's what we're seeing here. We're basically seeing the load imbalance of the different jobs causing still some lost time, right? Could you explain why seed $S instead of seed curly? That's because there's a typo in the slides. This $S here should say curly brace, set of curly braces. I just forgot to. I copied and pasted the command because, as you see, that's the same command with $S replaced by curly braces, but I forgot one $S, so excuses. So if $T doesn't work, some of these $T doesn't work, there can be a couple of reasons. One, you might have forgotten the T equals 2.2 here. If in that case, there is no $T, and bash, as well, I'll also expand on a little bit later, bash syntax is kind of funny. It isn't, things aren't quite as they seem. In bash, everything is a word separated by spaces. That's what there are no strings, there are no integers, it's just words separated by spaces. But if $T is not defined, say if that was the case, then there would not be a word here. And so it actually, what bound break thinks is that you want a temperature to be set to -seed, because the next argument is supposed to be the temperature. And so the whole thing doesn't quite work right. That's one failure mode that can happen if you forget to specify T. Another thing that can happen is that you might think that you have to put this whole command into quotation marks because it's one command. And that's not necessarily bad, except there's two types of quotation marks, single ones and double ones. And single ones will actually not change the value of $T into 2.2, whereas double ones will. So there's all these kind of little things that can go wrong. So I'd have to look at your actual test or your actual command to see what is the case here. But yeah, single quotes and double quotes are not the same. Good. Other questions? Okay, let's see some other issues that I saw when I looked at your proposals, your solutions. So a few things that annoyed me and that don't really matter too much for the solution, but it is something to keep aware of. Some people forgot a job script. So I got the output and I could see that something was done, but I didn't see what they actually submitted. Some people did the opposite and they submitted the job script, but not the output files. So then again, it was difficult to see what they got. And so I would have to run that myself. And these are short scripts, so it's not a big deal. But you can imagine in a more involved case, I would want to know both. Try to add one case of somebody submitted a screenshot. I can't try and rerun your screenshot as a JavaScript. So that's try to save things as plain text files. And when talking about plain text files, that does mean almost nothing that say Microsoft Word can create. So no rich text formats. They are not plain text formats. And so what that means is, and why I want plain text formats is that if it's not plain text formats, I can't read it or process it on the teach cluster. I can't resubmit it as a job because it's not a plain text format. That's what most utilities on Linux want, just plain text. Similarly, docx is not plain text. So it also means like if I copy this over to the teach cluster to look at your results, I can't even open it because Linux doesn't know what to do with an RTF or a doc. Okay. Anyway, those are just some gripes. They don't really change whether you did things right or wrong. But yeah, had to get it off my chest. So a .txt should work. So .txt should be plain text. .rtf is not. It will put all kinds of special codes in there that only, I mean, about the font to use and what should be bold and stuff, and it doesn't. It's not plain. So there should be none of that in the output. So just save it as txt. Make sure you click whatever you need to do to make sure there's only plain text. It can be hard to some text editors, particularly on Macs, say that they are plain text editors, but still put all kinds of special characters in. So that can be tricky. But that's not the case here. In this case, we had RTFs that I can't read on the teach cluster. So txt is typically what people call a plain text file. Don't just rename it. That's not enough. Obviously, you have to resave the message. Okay, so that's just some small things to. I managed to get everybody's submission in the end anyway. It wasn't a big hurdle. It's just something extra to do. Okay, so so what? A few things that went wrong and that did make things not work as they should. One particular issue that I've seen in a few cases is that you could just put parallel in front of the command. Basically, that is in itself not enough. And you also, so that would, presuming that the syntax is correct, start those jobs or collect those jobs. But you also have to have asked for the right number of resources. So remember, in these job scripts, there are really two parts. There's the part that gets done, but there's also the part that asks for the resources for the scheduler. And so if you do that part, asking for the wrong resources, what could happen is that you still got a single core, even though you're using GNU Parallel. So you were using GNU Parallel on a single core, and although 16 processes would be running at the same time, they'd also have to share this single core. So each of them runs at the 16th of the speed, and you get no speed up. So that's the symptom is no speed up. The cause is that you might not have asked for the right resources. So you can ask for number of tasks per node equals 16, and that should do the right thing. But again, it's a combination of the two. If you just ask for a number of tasks per node to be 16, and you did not use the parallel command, then again, it's not parallel. You were using 16, you were getting 16 cores, but you were using just one. So both of them have the same effect of basically no speed up. One, because you're not using parallel, or two, because you're not using the resources. And if you do, forget to take out the n tasks equals 1, which was in the serial case, it turns out that kills the parallelization too, because when Slurm sees both the number of tasks per node and the number of tasks, the number of tasks wins out. So you still got just a single core, which is something that is hard to know. It is a conflicting request, and Slurm does just sort of guesses that you mean one task and leaves it at that. So so get rid of the number of tasks equal 1 and submit it with n tasks per node, and use the parallel command. All three things. Another thing to note, and some people noted this, and this is fine, is that the output in the parallel case can be different from the output in the serial case in terms of the order of things that have happened. And that is pretty normal. When things run in parallel, the output to the screen or even to a file, as it happens now, just is done by whichever of the parallel processes happens to get there first. So there's no reason for, because here the different processes take different times, there's no reason for process 1 to be the first to finish. In fact, it won't. So you'll get a different order of your output, but that's okay because we were just interested in the collection of the output here. Another thing that I've seen happen a few times when we try to figure out how long something took is to try and time the command. And that works well for a command that you run on the command line. But if you do time and then your job script on teach01, which is where you log in, it runs on teach01 on the login node. And so that's not what you want. Now the timing starts to depend on who else is on the login node at the same time, and so basically your timings are unpredictable and do not mean much. So even if you want to time your code as it's running through the scheduler, so you'd say sbatch and then the job script name, you have to wait until things have run, and then you can use the sf command or there's other commands as control show job and some other ones, but sf is the easiest one for sure. And then just to stress a few things, the syntax matters for Slurm and also for Parallel. So the number of nodes is not the same as the number of tasks. If you ask for 16 nodes, that's not the same as 16 tasks. A node, I think by now you guys all know, we have nodes, and they're like multi-core computers. Each node has 16 cores, and so the number of tasks should match the number of cores for the task not to be for the cores not to be overloaded and for no cores to be unused. Right, you want those to match for best utilization. It also turns out, and although not many people did this, is that you should really also say -- nodes equals 1 on your job script. Otherwise, you might get more nodes, and it is even conceivable that some of your tasks would run on one node and not on the other. That didn't really happen because nobody asked for partial nodes, but that's like explicit is better than implicit when asking for resources. So it's good to say I want one node and I want 16 tasks on them rather than the opposite. Somebody's asking, executing on a command line, we use sbatch. Yes, so really what sbatch does, yeah, so that's true. To execute a job script, you do not execute a job script. Strictly speaking, the scheduler will do it for you, and you give it to the scheduler with sbatch. So sbatch and then the job script effectively runs that script, but not immediately. It runs it on a compute node whenever the scheduler deems it the right time for it. On the teach cluster, it's pretty quick, so it seems like you're executing it, but on a regular cluster which is busy, you would wait, and so you wouldn't be running it so much as requesting it to be run, and it will run eventually. Okay. The other questions were answered already in the chat, so let's see where we are at. Okay, a few useful tricks when you're using this. So this is what went wrong. This is now we're doing what can be done better. So in my example, and I would actually suggest it whenever you use GNU Parallel, is to use this -- job log command followed by a file name. And that file name will contain the log of the individual subjobs that GNU Parallel executes. So this is useful just in case something goes wrong. You run out of time. That means your job runs out of time, and the scheduler will stop your job when it goes on beyond the time it said it will. You can see which ones were done and which were not. You can also use that to restart things again, but again, that's a different slide. To get the timing for the whole script, the sf command is very handy because it's quite concise. It gives you the time it took, also the efficiency, so you know how well it ran. And this is kind of interesting, I find. So if you did sf on your serial job, it will give you a 99% efficiency, whereas on your parallel job, you will get something like 82%. So you would think that your parallel job is less efficient. That's not really the case, in that it's less efficient because of those last few jobs that there was nothing to do for. So the more jobs you have, the better that efficiency would be. It is as good as it could be. It just there's not enough work for it to be 100% efficient. But if you look at the timing, you will see that it should have sped up by a factor of about 12 or 13, or depending a bit on how busy the file system was. Another nice thing that you can do is you can actually add an email address and cases in which you want to get emails for your job. So especially if you're doing a lot of jobs that are usually okay, you might want to get an email when something has failed so that you don't assume they all went through correctly. So you can specify your email, you can specify when it will send. So in this case, if I set mail type to fail and end, it will give me an email when it fails, but also when it ends. I could also add begin, and then it will tell you when it began, if that's very essential for you to get an email about. You don't have to do that. The default is getting no email, but it could be, especially failures might be nice to know about rather than having to look at the job logs. Another thing that I like to do in job scripts, I didn't do it in the one that I showed, is to make sure that they fail quickly when they fail. So since you're submitting a job script, and in realistic cases, that job script won't run for a few hours or sometimes even days, depending on how much you ask and how much you've used, it's basically just running without supervision. And if there's an error in like the first line of your script, by default, the script continues to go on with the other lines and tries to compute those. And so it might be that it takes the whole, say, 20 minutes to know that something went wrong when what went wrong was already in the first minutes. So there's two things that you can do there's a couple of things you can do to change that so that whenever there's a failure, it stops. One is just to use the set-e command and in your script, and that tells Bash whenever there's an error, just stop running the script altogether. And so that's great. If a command fails, for instance, you have misspelled the name of a module and you said GNU parallel with just one L, it will just fail there and not try to continue. And another thing that is a common cause of errors is that you have a variable, say the variable t, but you're using it as $t, but you never set it to a value. So it's an undefined variable. Usually, Bash just submits, glances over that and says, well, that's an empty string, or it's really just nothing. So that can sometimes be useful, but in many cases causes errors that are hard to understand. If you add set-u, then whenever you have an undefined variable, Bash will print out undefined variable and stop your script. Well, it will cause an error, and because errors causing the end of the script now, it will end it. So set-eu, because you can combine the e and the u, will make sure that if something's wrong with your job script, it won't go on beyond that error. There's a few questions in the chat, so I'm just going to look. One that is immediately related to set. There's a set-x. What that does is it actually prints out every command that is in your script. So normally when you run your script, you don't see the commands of your script, you just see the output. If you add -x, you also see the commands that are run, which can be useful to debug. But if you have a lot of commands, it can also be just too messy. So it depends on what you want to do. But it's not bad. Like you could do EUX, and then you get the best of all of those things. Yeah. So something I didn't mention, but was on the slide. The syntax with the 3 colons is not a syntax element that Bash knows about. It's just a special argument that GNU parallel uses. And because it has to be its own argument, it has to be separated by spaces on both sides. Otherwise, it's not a separate argument. So, so colon, colon, colon here is not a syntactical element. It's really just a command line argument that means something to parallel, but not to the script. So if you look at the solution, if you didn't put a space between the 3 colons here and the curly brace, it would not have worked. It doesn't know that there's a break because it has to have a space in it. So spacing matters. It's one of those odd things that Bash does. Yes. And the single quote and double quotes, again, it matters. A few other tips. I have a whole slide about Bash-related weirdness. It's not weird. It's just different than you intuitively might expect. But we'll get to that very soon. Don't copy and paste, especially not from PDFs. Don't copy and paste just whole lines, and you don't know what they do. you just run them, you batch your JavaScript with things in it that you don't understand. That is a recipe for disaster. They will likely not work because if you don't understand them, they're probably either not needed or they won't necessarily do what you want. So if you look at our wiki, you will find a lot of JavaScript examples, and they might say things like module load Intel 2018.4 or GCC or something, and you might just copy and paste them, going, I don't know what they do, but they have them in the example. They're probably needed. Try to understand what they do, because if you don't know why you need them, you might not need them, and they might actually interfere with things that you do need. So just try to understand what each line does, and don't copy and paste until you understand what that line does. Relatedly, and this is especially true if you've played around with things on your own computer, be wary of any recipes you find online, like installation recipes, Slurm recipes. If they don't come from either Compute Canada or Cynet documentation, there's a good chance that they won't work. Even if they say this is how you do something on Linux, and all supercomputers run Linux, still they make assumptions on what kind of computer you have. They make assumptions on what you're allowed to do in that computer. Essentially, most of these recipes assume that you are working on your own machine where you can install anything you want, and there's no other people that also need to do. And also they assume that, say it's an installation recipe for, I don't know, R version 4, they assume that there's nothing else in the way and that you don't want another version as well. So there's a lot of assumptions that go into that might work very well, and if indeed you're working on your own computer, but that just will not work on a shared machine. You can't just write to any place in there which would have effects for the other users. You wouldn't want another user to change the configuration of the system, and then suddenly your scripts don't work. So this sharing, again, of the shared resource that we have here means that things work a little bit differently. It's almost never impossible to get something done, but the recipes might not work. So those are some tips. So let's talk about Bash. So Bash is a funny language. So Bash is the Linux shell that we're using, right? So it's /bash. It's a funny language because really everything is a string, or everything is just a string, but a string of words. As soon as there's a space somewhere, Bash will consider them as separate arguments, separate words. And so if you have a command that you give, and you give it a string, and there are spaces in the string, then those are now multiple arguments rather than one argument with spaces. Spaces are actually not that hard to put into a single argument. So basically, to stop this breaking of a string into words, you can use quotation marks. So that is one way to, as they call it, escape your spaces, is to say put them in quotation marks, either double or single. And if you do that, the space will not cause a break. So now the whole string is seen as a single argument. Okay. But there's two kinds of quotation marks. And so if you have a variable and you want to use its value, you have to say $, and then the name of the variable. So we saw it for t equals 2.2, does assign 2.2 to t as a string. There's no integers, just basically it's one word, 2.2. $t will give you 2.2. But if you have it inside the string, it only works in the double quotations. So double and single quotations basically protect your spaces, both of them, but the single quotations also protect your $sign. So if you ever wanted to really pass a $sign as an argument, that's the quotation marks you would use. You would do single quotations. In many cases, you don't. You just want this substitution to happen. You have to put in double quotation marks. There's another way to escape your $signs, and that's to prepend it with a slash. So that's a very explicit way of saying this particular symbol, dollar, should not be used as if it is a variable. Just this is a literal dollar sign. Okay. You can do that with quotes too. So if you wanted the quotation mark as a variable, sorry, as an argument, you have to do slash and that quotation mark. Okay. Another funny thing that happens, and this bit me a few times, the ranges. So those are the curly braces 1.96 curly brace end that we had. They are expanded, but they're expanded before variables. So you can actually not use variables in those ranges, which I find very annoying because I would like to have 96 in a variable, and it just doesn't work in this case. And it's just how Bash does it. It first expands the ranges and then the variables. And then there's two kinds of variables, which matters if you have bash scripts calling other bash scripts. And at least one of you did that. So when you set a variable like t equals 2.2, in that same bash script, that value is present. But if you called another bash script, which you can just do by calling its name, that script will not inherit that variable unless you've exported it. So there's an export command that you can use, export, and then the name of the variable. And then that variable that is set in the current script will also be known to the subscript, okay, or subprocesses. So those are all things that you kind of have to sometimes know, because things go wrong and you think, why do I not have a t variable in my subscript? And the reason is you didn't export it. Or why am I not getting my $t's? Because I have single quotation marks and not double ones. Yeah. So it really, to understand this, you have to think of it as Bash is just words. And if you want words to contain spaces, you have to do something special. If you want words to contain dollar signs, you have to do something special. If you want dollar signs to, or if you want variables to stick with you, you have to export them. And it's it looks like a standard programming language, but it is kind of funny. So the way I kind of use Bash is to try and use the single quotes as little as possible. So only if I really want to make sure that there's no variable expansion. By the way, also file name expansion, things like the star operator does not work in single quotation marks. Only if I really want to stop that do I use single quotation marks. So I usually just do double ones or none at all. If you don't need quotes, don't use quotes. Right? So you use double quotes really only if you know there are variables in there that might contain spaces. So you do have to keep that in mind. Spaces could happen. But this is another reason why we often say, when you're using file names, don't put special characters in there. Don't put spaces in them. Don't put dollar signs into them, stars. Because if you use those variable names unquoted in a script, funny things can happen, right? It doesn't mean what you think it means. So it's proactive to say your file names should all have basically plain characters, and none of these special things that mean something to Bash. If you want a space, why not use an underscore? It looks the same. That's kind of what I do. There's one value. Let's see. Yes, there's one question left here with the error in command line file name. So let's go back to the. So if you put this, let's see what might have happened. Yes. If your file name, so the order of these, okay, what somebody is seeing is that a complaint that the file name is not correct. It seems to be, but no, what it says, it's an incorrect argument file name to C. So if your $S does not exist here, and it wouldn't, because this should be curly braces, but say I left out the curly braces here, right? Yeah, I'm hoping that that's not the error here. So this $S should be curly braces. That it's just a typo in this answer. All of the $S's should be curly braces. If I leave out the curly braces or leave out the $S, dash just seed will take the next word as its argument. And the next word is dash dash file name, which is not a valid argument. Like it's not a seed. It can't be converted to a number. The seed should be a number. So bound break will check if what is given to seed is a number. In this case, it isn't. This dash dash file name, which is not a number. And that's what it complains about. What it means is that this arguments to dash dash seed is for some reason missing. It could be missing because S was not defined. It could be missing because we don't have curly braces. It could be missing because $S contains an empty string, and that would have the same effect. Yeah, but what the command is saying is that since file name is now swallowed by dash dash seed, something is wrong with the argument of dash dash seed, and that could be also because we have yeah, it could have a number of reasons of why the command was expanded in that way. Any other questions that we got? And I know Bruno is helping this user here, so that's good. But any other either bash or parallel related questions, things you saw that you didn't quite understand? That's a good question. How does parallel know when the last argument is given to it without quotation marks? So let's go to the example here. So why does it know to stop here? And so basically, it stops when it sees an argument that is : : or there's no more arguments. So the way it wants to, so all of the options that are given to parallel. So there's one can think of two kinds of options. There's options that have dashes in them, and they usually have an argument to them, sometimes not. And then there's just plain words, right? So in old-fashioned Linux, the ones with the dashes always had to come first, and it's still not a bad way to do it. So what GNU Parallel will do is it will read in arguments. If they have a dash in them, possibly with an argument, it's not part of the command. It's just part of an option for parallel. So that's dash job log here. If there was another argument, say -J8, that would mean it's an other option for parallel to set the J argument to 8, which is actually the number of simultaneous jobs. Then as soon as it sees something that does not have a dash in it, and is also not an argument to an option, so as soon as it hits bound break, it says, oh, here is where my command starts. Everything else, including things that have dashes, will now be seen as part of the argument. So it really sort of puts a hard break after the last dashed argument and says everything else is a command until the end of the line or until triple colons. So that's why I didn't really need quotation marks here. If I did double ones here, I think it would have worked just fine. But it wouldn't have hurt. Basically, it would have said that this is a single argument to GNU Parallel, but that for GNU Parallel is the same as having a bunch of words as an argument. So the end is the end of the line or triple colons. Any other questions? You can keep asking questions. That's fine in the chat. But I think I'll end. We have about half an hour left with some tips on best practices in scientific computing. And so these really are things that are better known ahead of time than learning it by doing it wrong first and losing a few months of work because you didn't follow these best practices. And believe me, that happens. The first thing to realize, and it doesn't sound true, but it is, that code doesn't die. There are no one-off codes or scripts. So that JavaScript you just created, guess what? Next week, somebody asks how to run on a supercomputer. And, well, I have a script. Here's a script. It lives on, right? If it was worth running and writing, it's worth doing it again. And so almost surely somebody, and it could be you in 6 months, will use it again. There are no one-offs. And so that puts sort of a burden of maintainability on you that you either do ahead of time, in which case it's actually pretty easy, or you try to figure it out later. So if it's a big, ununderstandable mess of a script, even if it worked, no one will want to touch it. You will not want to touch it in 6 months, try to figure out what it is. So you have to basically rewrite it. So the only code that dies is code that is unmaintainable and just not worth looking at. The fact that it worked once doesn't matter. So working of code doesn't matter. It has to be reusable for it to be usable. Now, in the world of professional software developing, professional software developers deal with it all the time, and they know what to do. So a lot of these things just come from good software development, but some of these seem to be a little bit overkill if you're just trying to get something computed. That's right. Like most of you are computational scientists. You compute things to do science. That makes you a computational scientist. And you just want your results. You want your script to work, and that is point one. But then often that's the last point. Whereas professional software developers know that this code, this script will be given to customers or other people in the team, and so they will get back any issues that are with it. Okay, so if you put in a bit of effort to writing maintainable, reproducible code, people won't get back to you saying, "Hey, can you please explain this or rewrite the whole thing?" And your code has a chance of being useful for yourself or for others. Okay. So what kind of things can we do to make code live? So one of the things that you can do is to automate everything, automate all the things. Whatever you do should be documented, but a lot of the things you do are just commands. You type on the command line or things you did. So try and write scripts for any computation or any data processing you do. The nice thing about having to write JavaScript already is that it sort of forces you to do that, rather than just run things on your command line and go, well, I got these answers. How did you do it? Well, I don't know. I think I did this and this. There's no thinking. There's no remembering. It's in the scripts. So keep your scripts. Don't throw them out after they're run. They're a way to rerun the same thing or a very similar thing, right? You have a precise record. You can rerun them. So this is harder to do if GUIs are part of your workflow, so graphical user interfaces. You would have to say, click on the second button from the left. And you don't want to have to do that because GUIs also are quite prone to changing. So if you can at all, try to not use any GUIs. Try to replace it with commands. In many cases, that is possible. Right? So it's hard to keep a record of what you do in a GUI. If you're building software, use a build system that explicitly says how you build your code. Makefiles can be perfectly good ways to do that. CMake is another system that does it. There's a variety of them. Some are better than others. Some we hate, some we like, some we love. But just at least make sure that it is automated and reusable. So that if you ever get this script or find the script 6 months later, you don't have to figure out how to run it, how to compile things, or anything like that. Second tip is to use version control, because if you don't, you're doing it wrong. So what is version control? It really is a tool to manage changes in files, and it works best on text files. Think of a script. You have a script, you ran it, something was not right, or you want to change something, but it's just one line that changed. Version control can keep track of those changes in the file and say when somebody made a change to what file and hopefully why. So it keeps a historical version for easy tracking, but it does it file by file and line by line, which means that you don't have to copy all of your workflow from like every time to say a new directory or say this is the version of November 11th, this is the version of November 12th, and just have a whole bunch of those, which is a version of version control, but it is a very poor man's way of doing things. So it's not enough just to have a history of your commands. Somebody's asking if our history is no, I don't think so. unless it's a package that I'm not familiar with. But no, version control should live outside of your programming environment, because you are keeping track of things in a, say in this case it's R. If you have if you're working in R and you want to keep a track of what's changing in R in your R script, then that doesn't happen in R, because if it also happened in R, now you have to keep a version of what's happening when you're keeping track of R in R, which means that you're doing that in R, so you have to keep track of the things that are keeping track of the things that are keeping track. To stop the recursion, you want to step outside of your programming environment. So one way to do it is to use a version control thing called Git. It's very common. SVN, CVS, those are other ones. Mercurial, it's not bad. They are basically applications that store your files, store the old version of files, usually in a hidden directory of sorts. They are now repos. They could also be hosted online. You could host them in GitHub, GitLab. You could host them yourself so that they aren't actually anywhere on the cloud or on the web if you want that. But the point of them is to keep a track of the versions, to be able to say undo a suspicious change, to also know, because most of the cases, if you make a new version and you store that version, you have to put a message there that will explain what you were doing. So it'll also give you a way to sort of document why a change was made, and that can be very useful. It can also make it easier to collaborate on code. So especially for instance, Git, two different people could be working on different parts of the code at the same time, and then this version control system has a way to merge things. And unless they are touching the same files, those will just sort of seamlessly happen. It helps you to stay organized, track changes in code. It also means your code is more reproducible. So suppose you ran something last month, but then you worked on the code and you changed it. But the month later, your manuscript comes back. Reviewer says, "Can you please rerun this because I'm not quite sure this is correct." You can go back to the version you were actually running. You don't have to worry about whether any of those changes changed anything in your results, because you have a record of every version. Okay. So this is a reproducibility issue. It's also a sort of a backup system in a sense. You have to back up your files separately anyway, but it means that your versions are all there. So something goes wrong, you made a lot of changes in your code. Because it's in version control, you can just go back to the last working version, and you lost a few days of work, but not all of your work. So it's very, and it's something to get used to. It seems like a bit of extra work initially, and it is, but you get used to it very, very quickly. So if you don't have a version control system in mind, look up Git. It is somewhat cryptic, but it is widely used, and therefore it's very easy to find information on how to use it on the net. Okay. So third thing, comment and document everything. You must document your code. So the answer that I gave for the assignment is actually wrong because it didn't have comments that explained what I was doing. You have to do this. This is not optional. But there's different forms in which this comes, and you might add your documentation at different levels or different stages in your initial start of a project. But one form of documentation is to have sensible variable names, things that make sense. The temperature in our script was called T, capital T. That's a common name for it, at least in science, so that makes sense. If we had called it X, how on earth would we know what it means? So sensible variable names. If you have functions, classes, modules, give them sensible names. But even so, T could be time, could be temperature. So you might want to add a comment in the code that says what it actually is. So comments in the codes are very helpful, and so put them in. If you're writing your own modules, own functions, you can document them further with help commands or doc strings or other ways that you can add information into the code. The code wouldn't change. What is actually executed isn't changing, right? For the computer, these are not important things, but for the humans reading this code and changing it later, that it is very important. Right? because you don't really write your script just for the computer. You write it for yourself. If you wrote it for the computer, you would write it in assembly. It would take you forever, but you don't care because the computer is all that cares, and that's all you would do. This is not what we do. We have we're dealing with humans here that have to run this code and maybe have to run it again. It might be you 6 months down the road having to rerun this or change a little bit. If you didn't write comments, didn't have some sort of documentation for what your scripts and your workflow is doing, you after 6 months, believe me, you won't remember all of the details. Right? So in the very least, when you have some scripts, have some workflow, write a little README saying what it's supposed to do, or if it's something that you are going to distribute and it is somewhat complicated, write a full manual. Don't trust just applications that automatically generate documentation for you. They can be useful, but they can't be the only thing, because if it wasn't clear from the comments that you put in your code how things fit together, people won't figure it out. By the way, I don't believe in self-documented code. It just doesn't exist. It's called code for a reason. Code means we're encoding something in a language, right? If it's codified, it means that there's a key to uncodify it, and so it's by definition not documented. It's good to try and be as documenting as code as you can with a sensible function, variable names and stuff, but this is never just enough. Okay, point 4, try to make your code and scripts portable. So one of the things you should always do, if you can, is if something works on one computer, try it on a different computer, try it on a supercomputer, try it on a different supercomputer, try it on your girlfriend's computer. Why? Because if it doesn't work on another computer, first of all, it's very likely there's a bug in it. So you just found a bug, and so even though something might have worked once, it might not work again. But you might also at some point have to take what you're running now, even though it's at a small scale on your own computer, to run it on a supercomputer, and suddenly everything breaks. So the earlier you can keep things portable, the less work it is later to make them work on other machines. One of the ways to do that is to not hard code paths. So your home directory tends to have different paths on different machines. If you put in /home/l/lcl in your script now, etc., then this script just won't work on your own machine where you don't have that directory. Many systems have some variables in which they store common paths, like $home would store where your home directory is. Use those instead, so that if you go to another Linux machine, that script has a chance of working. So don't hard code paths. Keep relative paths too. So in Linux, you can either start from the very root of the file system, so you have /home/ etc. But often you can do it relative too. So if you're already in a directory, you can refer to a subdirectory just by the name of the subdirectory, not by the full path. So don't hard code paths. Don't do absolute paths. Try to use shebangs. So shebangs are these first lines in scripts that basically identify to the operating system what kind of script it is. You just run it with Python, with R, with Bash. But Bash, Python, R, they don't live in the same path necessarily. And unfortunately, you have to specify the absolute path in the shebang. So we've seen pound $bin/bash in the solution. So /bin/bash is the absolute path of Bash. And while this is true on almost all Linux systems, it's not true on all of them. And so there is a way to make it a little bit more portable using a command called env. And so /user/bin/env, and then followed by, say, bash, will find bash in wherever it's supposed to be installed. This is probably about 99.5% reliable, whereas the previous case was maybe 95%. So it's an added thing, but it especially helps when you're dealing with not so much Bash, which is very standard, but things like Python or R or Julia or things like that, which might be installed in non-standard paths. So this is a useful utility to make things more portable. Make as few assumptions as possible if you can. It's hard to say what this could be, but say you're running a Python script and you're just assuming that it has NumPy. Well, if that's the case, don't write your script just assuming that. Have in your documentation somewhere an explicit statement that says this requires NumPy, or this requires this or that packages. If you don't really need them, do not use them. So use as few assumptions as you can. And this is hard, but just because it works for you doesn't mean it works everywhere. And finally, stick to standards. The programming languages have standards, especially things like compiled languages, C++, Fortran, that compilers have to be able to follow. But a lot of compilers and even a lot of scripting languages have sort of exceptions to them, where they say, well, you know, we always used to allow this, so we're still allowing this non-standard thing. If you use them, what that means is that you go to a different computer, different compiler, it doesn't work. And so just try to stick to what seems like probably the common lowest denominator of the programming language, but it's the one that will work everywhere. And so avoid the but it works on my computer bug. Just because it works on your computer, if it doesn't work on another computer, yes, sometimes that other computer is wrong, but if we've got already 1,000 people working well on that other computer, maybe it's not the computer's fault. So, and often it's like little differences like that you don't want to have to trace down. Okay, another point which comes to play when your workflow or your code gets to be pretty large, and this is true for most scientific software. Even if all that you have is a bunch of scripts, they're probably calling a slew of different applications in different ways, and you try to modularize, by which I mean separates your code, your scripts in little parts that do one thing well, so that and that then can call one another. And this way, you don't have a single script that is 2,000 lines, where if something goes wrong, any of these 2,000 lines could have been affected by any of the other 1,999 lines, but rather you find that the error is in one of your subscripts, which is 10 lines, and then you only have to look at those 10 lines for what is wrong. So it really helps debugging things or keeping things maintainable. If you want to change something about, say, the way things are written to file, and that is a separate module, you only have to look at that separate module, and you don't have to worry about anything else breaking. So modularization is a way to keep yourself sane when working with large, complex, and subtle scientific software. By the way, if it's modularized, you can also test things. So if you write code, you should write tests to check the code. You can never write the tests exhaustively, because the only way to do that is to actually solve the problem you're solving anyway. But that isn't an excuse not to have any tests. But writing tests for modularized code is a much more productive way to go, because if the tests for that one module fail, you only have to fix that one module. If the test for your whole application, your whole workflow fails, you don't know where to look. So again, this keeps things very maintainable. And so how you go about this it's a bit of an art, but the idea is that modules should have one single specific task, one responsibility, right? So maybe it's I/O. There's a writing in files, or maybe writing and reading to files. They are related tasks. One could be doing a computation. One could be fetching things from the internet. Like it could be modules doing different things. Separate them into different files also means that you can, first of all, find the errors easily and fix them easily, but also better use things like version control, because you could roll back just one of the modules to something that worked before if there's an error. Another thing that is good to have, and this is true actually regardless of whether you write scripts around existing applications or your own applications, is to do a thing called checkpointing. What is checkpointing? Well, checkpointing is a solution to problems that happen while your job is running. So we have situations where, or we have a situation where we submit jobs. They don't run immediately. They run without supervision on some node or several nodes, and things can go wrong. For various reasons. Your job might have a spelling error and it fails, or it might take too long and be killed by the scheduler, or it might take too much memory and then be killed by the operating system because the memory is simply not there. There could be something wrong with your account. Maybe you're running out of disk space. It can happen in the middle of a job. You filled up your home or your projects or your scratch space, and it crashes your job. It could be due to the system. Sometimes there's file system issues. It's not that common, but it happens. And so or it could be some external infrastructure, like a power outage. In all of these cases, say your job took 12 hours to run. That's what you asked for. And 6 hours in, something goes wrong and it crashes. You don't want to have wasted those 6 hours. If there's a way to stop the job and resume it once you fix whatever was wrong, particularly if it's system or external things, then there really should just be no issue resubmitting. But you have to be able to skip those first 6 hours that you already computed for. So there has to be a way to save your intermediate results to disk and being able to reread that so that you can start from the 6 hour point on. Right? So that's checkpointing, doing periodic writes of a checkpoint that has enough information to resume from that point. Okay? That's what checkpointing is. Now, it is theoretically possible to have the operating system do that. So you might imagine, well, why doesn't the supercomputer do this for me? If it crashes, it just checkpoints the state of all nodes and then resumes when things are well again. And the problem is that is very inefficient because you would have to store so much information on the whole operating system that, first of all, it takes an enormous amount of time just to write all that information. But second of all, you don't need it. You probably only need a few things to restart, and only your application or your script knows what it is that you need to be able to restart. So it's your application or your script that needs to be able to implement that feature. A lot of standard applications have this. Like if it's an out-of-the-box application, they will be able to do that. GNU Parallel has it too. In a sense, if you use a job log, it not only keeps track of all of the jobs that started or failed. That also means that you can rerun the same GNU Parallel command, but now add the -- resume, and it will skip over everything that was already done, and just do the ones that were left. So even GNU Parallel has that feature. What it can't do is to checkpoint the subjob. So a subjob was already running, it crashed. That means that in the log, it will not show up as having been completed. And there's no way for GNU Parallel to know how to restart that subjob. It would have to know, it would have to be able to do that inside the subjob. But that it can still resume and just restart those. So this protects you from a lot of wasted compute times, and especially if you're doing a lot of large scale computations is extremely important. It's also worth mentioning that most computing sites have a limit on how long you can compute. So for Niagara, that's 24 hours. For say Beluga, it's I think 7 days at most. And that means that sometimes you have a computation that takes longer. If it doesn't checkpoint, basically they won't allow you to run it. So you have to be able to checkpoint so that you have one job of 24 hours and then restart it in the next job of 24 hours until your job is done. And that is totally feasible and actually a very robust way to do it, because if there is a crash, you haven't lost a month worth of computation. Same point again that I'm making. So it's a good thing to have, but it is something that is sometimes just, there's no way around it. You have to do this to get your computation done. Finally, one thing that I haven't stressed too much, but I should have, is that in this supercomputing business, one has lots of nodes. The nodes tend to be of a fairly recent architecture, so they're fast cores. although most of they have many cores in each node, that's great. They have an interconnect, so a network that connects the different nodes that is very fast. The part that is the slowest of the whole system tends to be the file systems, and that's just essentially a physical limitation. Home, Scratch, and Project are the three directories that you typically have on Niagara. On the teacher, you have Home and Scratch. They all use a parallel file system, and it's not that that is like slow. It's just that it is shared among all those nodes. And while we could design a file system that is so fast that no matter how many nodes are doing, say, output at the same time, it will always be performant, that itself would be a waste, because most computations are such that there's some computation, there's some output, so computation, some output. So the way that this is designed is to be able to write occasionally, but also when you write, to write in a parallel fashion. So you might have a big application, say it's a weather simulation, and at some point it has to do these checkpoints, it has to dump the whole system state. This is a fine grid, so it's a large set to write, and it's already computing on several nodes. All those nodes can write to the file system at the same time in parallel, and it's nice and fast, but it only works if it really is a parallel write. Right? It's meant to do large data sets in parallel from many nodes. What it doesn't do very well, because it's not designed for it, is many small files. So as I said, one can make file systems that do that. They're just so expensive that you have no more budget for actual CPUs. So this balance of having a shared parallel file system means that what you should do, as you shouldn't do, is you should try and write large amounts of data to disk at one time. So don't write little amounts of data. Don't have many small files. It's just not something that these file systems are good at. I mean, any file system would eventually choke, and it's often also not something that's really desirable. It might be something that works out of a workflow that you had, and you scaled up, and now suddenly you have 10 million files that you want to create. But think about it: are you ever going to individually look at those 10 million files? No, there's another application that will somehow analyze that. So it doesn't really matter that it's 10 million files. It might as well be one large file with all of the data in it. So why not do that, right? So try and create larger files whenever you can. So you don't waste space and don't have slow access. Another thing that helps in I/O is to make sure that things are, like if it's numerical data, to write it out in the format that it is stored in. It takes less space and it's faster. So for numerical data, that would be writing out in binary. So don't write out in text if it's numerical data. If you have text, write it in text. That's the fastest way. If it's not, if it's numerical, write it down in numerical, which is binary for computers. Okay? Some file systems are better for I/O heavy jobs. So if you are running on Niagara and you have a case where you know, well, I've done my best, but I still have to do very many I/O operations per second, we have a file system that's better, that's called burst buffer. Some systems have node local storage, so basically local disks. The nice thing about that is that even if you're doing heavy I/O on those local nodes, it doesn't affect the rest of the file system, the parallel file system. And so that's a way to at least make sure that while it might be slow, only your jobs is slow and it doesn't affect the others. Okay. Another nice thing you can do is, if things fit in memory, you can use what's called a RAM disk. So if you have heavy I/O, so you're creating lots of little files, but maybe they're temporary files. It's just how your workflow works. But your first thought would be just to write those files to, say, the Scratch directory. You can also write them to what's called a RAM disk, and that lives in memory. It's local to the node, and it's much faster and doesn't affect the rest of the file system. So that's a great way to go when things fit in memory. There's a question here. If you submit a job and then cancel it before it runs, will that also affect your priority, or only when you're running? So we're talking now about the things that affect your priority. And the way things are set up, in virtually all systems I know is only things that you used are counted are accounted against your usage. So if you submit a job, it hasn't run, and you cancel it, it's like it never existed. If you run a job and it is 12 hours that you said it should take, that's the time parameter, but it finishes in 6 hours, and so it reached the end of the script, then 6 hours is accounted towards your usage, not 12 hours. It's just whatever you use, that's what's used. But if you have a script that you say takes 12 hours and it's a full node, in this case 16 cores, but you use only 1 core, you're still dinged for the 16 cores because you're keeping 15 cores idle. So whatever you reserved, the time that you actually got that reservation for, is counted. Okay, so that's the end of my spiel here, the end of my tips. Don't forget to take the attendance test. If it's still giving you trouble, or if you timed out of the number of times, just write your username in the chat quickly so that we can make sure that we know that you didn't all log in with your usernames. So we wouldn't know who you are. But the best thing is just try the attendance test. 5 should be the number there. If you haven't submitted your assignment yet, but you've got more ideas now, make sure you do. You have a week's time. And also don't forget, there's a evaluation survey. If you go to the place where you took your attendance test, there should now also be a button saying, here's an evaluation survey. And we would be very happy if you would want to fill that out. It shouldn't take more than about 10 minutes or so, if that. And it will help us make these kind of workshops better in the future. And happy computing. You're all very welcome.